Good day, grade 12 learners. Welcome to today's technical science lesson. My name is Musa Zulu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. All right, grade 12, today, our knowledge area again, we are doing matter and material. Still on matter and material as we were on last week. The topic of the day again today is also organic chemistry, but specifically in organic chemistry, today we'll be trying to look at IUPAC naming. So basically, we're going to be trying to naming these compounds or teach each other how we go about naming these compounds, which is probably the most important thing that you can learn when it comes to organic chemistry. Naming is very, very important. Grade 12. You will find most of naming in question 2 of your paper 2 question paper. And question 2, grade 12 is a very, very important question. This is the question that is going to either help you pass or you are not going to make it if you do not know how to master question 2. So question 2 is very, very important to me. And mostly what's important to me with regards to question 2 is people must be able to draw structural formulas, and they must be able to come up with molecular formulas. And especially people must be able to identify homologous series, and people must be able to name. They must be able to do IUPAC naming. Extremely, extremely important in question 2. Question 2 is important for us passing paper 2. All right. So lesson objectives for the day, grade 12. By the end of this lesson, I hope you must be able to, well, first distinguish between saturated and unsaturated hydrocarbons. You'd remember that the previous week we spoke of hydrocarbons, what they are, and we defined what hydrocarbons are. Today we'll be distinguishing between saturated and unsaturated hydrocarbons, telling us that there are two types of hydrocarbons, those that are saturated and those that are unsaturated. So we must be able to distinguish between the two. And then we must be able to define the different types of isomers. So we are going to also look at what isomers are, and we are going to look at their different types. How many types of isomers do we have? And we are going to differentiate between all those isomers and define them. And then lastly, which is again very, very important, I want you to be able to use the homologous series and the functional groups to do what? To name. I want you to be able to name organic compounds by using the homologous series and the functional group. So you identify the compound by its homologous series, and you do this by looking at the functional group. All things that we discussed in the previous week. Okay, so pre-knowledge or knowledge that will be needed for you to be able to understand today's lesson, you must be able to define what organic molecules are. We defined what organic molecules are last week. You must be able to define a homologous series, a very, very important definition, this one. Extremely, extremely important that each and every one of you is able to define a homologous series. You must be able to identify from which homologous series does any structure belong. So given a structure, for example, you are given a structure like this. You are given a structure like this. Okay, and then from this structure, you must be able to identify from which homologous series does it belong. And how do you do that? By checking its functional group to say this structure has a double bond. And if you remember last week, we said by me seeing a double bond, I will say this structure belongs on alkenes. So this homologous series of this structure will be what? Will be an alkene. So you must be able to do that. This is again what we talked about last week. You must be able to write structural formulas. You must be able to write molecular formulas. And you must be able to write condensed structural formulas for all organic compounds, for any organic compounds within the 9 homologous series, of course. And lastly, you must be able to define hydrocarbons, as we've spoken about that we spoke about hydrocarbons in the previous week. And today we want to speak about the difference between a saturated hydrocarbon and an unsaturated hydrocarbon. So that shows you right there that before you can distinguish between saturated and unsaturated hydrocarbons, firstly, you must be able to understand what the hydrocarbon is. So that means you must be able to define a hydrocarbon. So that's the knowledge that is going to be needed for you to be able to master today's lesson. Okay, so with that being said, we're going to take look at a little bit of a baseline assessment, just some few questions that are going to help us ascertain whether we know these things that are expected of us to know before we dive into today's lesson. For example, question number 1 is say, define the term organic molecules. And we defined the term organic molecules as organic molecules last week as organic compounds containing carbon atoms. We say these are compounds that are containing carbon atoms. We even said last week that tells us that when we're dealing with organic molecules, the central atom is going to be carbon. The central atoms around organic molecule is going to be carbon. And then we want to be able to define a homologous series. Question number 2 says, define a homologous series. And you should be able to define a homologous series, grade 12, by saying this is a homologous series. And then consider the following structure and identify the homologous series from which they belong. So you look at the structure, and then you must be able to identify from which homologous series does this structure belong. So you look at the structure, that means you are going to check its functional group, and then you are going to determine from which homologous series does this structure belong. And then the next question there says, write the molecular formula and the condensed structural formula for the compound above. So by looking at the compound above, last week we spoke about how you formulate a molecular formula by looking at the structure. If you remember there where we were counting all of these things. So these are the questions that I need you to be able to answer for you to be able to master what I want us to do for today. And then the last question says, state whether the compound above is a hydrocarbon and explain why you say so. So you, by looking at the structure above, are you looking at the structure, are you saying, is this a hydrocarbon? And if the answer there is yes, then you must explain why you think this structure there is a hydrocarbon. Okay, so looking at the first question there, define the term organic molecules. As we have said there, these are molecules that are containing carbon atoms. These are molecules that are containing carbon atoms. And grade 12, be careful here. We do not say containing carbon atoms only. We do not put the only there. Most of you will make a mistake here and confuse defining organic molecules and defining hydrocarbons. When you're defining hydrocarbons, the keyword only there is important. But when you're doing organic molecules, you do not say only. Remember, organic molecules do not only have carbon atom only. They are centered around carbon, yes, because carbon has that ability to form long structures, as we said in the previous week. But they do not only contain carbon atom, but they contain carbon. They must have carbon. Okay, the next question was saying there, define the homologous series. Then we say there, this is a series of organic compounds that can be described by the same general formula and where each member differs from the next by a CH2 group. That's how we define a homologous series. A very, very important definition there. Very, very important that you should be able to do this differentiation. And the next question was saying, consider the following structure and identify the homologous series from which they belong. So to what homologous series does this structure belong? So if you remember, we had those 9 homologous series that we spoke about last week, and we spoke about their structures of the functional group, which is extremely, extremely important. So by looking at the structure, you should be able to identify to which homologous series does this structure belong. So by looking at it, you should be saying that this structure belongs to alkanes. The homologous series that this structure belongs to is alkanes, because this structure consists of single bonds between the carbon atoms. Okay, and then the next question there was saying, write the molecular formula and condensed structural formula for the compound above, right? And to write the molecular formula, remember grade 12 that we said, you simply go there and count the number of carbons, 1, 2, 3, 4, then write C4, and then after that you go and count all the hydrogens that are around, making that carbon happy. If you remember that we said carbon is happy when it has 4 bonds around itself. You should find that the molecular formula is C4H10. C4, 1, 2, 3, 4, H10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you have 10 hydrogens there. And then you're also asked to determine the condensed structural formula for this compound that is above. And then to do the condense, you simply just remove the bonds. You are condensing your structure. So just remove the bonds and write the carbons and the hydrogen. So the first one would be CH3, and then you have CH2, then you have CH2, then you have CH3. You would remember that you also have another option here of writing it as CH3 and then opening a bracket and saying CH2, 2, indicating that I am having two CH2s here. So you have an option of writing it like this, CH3. However, I would not recommend that people write this one. I would recommend that people write this one because it comes directly from the structure. As I was advising last week, that everything must be centered around the structure. Everything must be centered around structural formula. So even the condensed structural formula must come directly from the structure. So that even when you do the reverse of drawing a structure from the condensed, it should give you there should be a direct relationship between the two. Okay, last question there is asking us to state whether the compound above is a hydrocarbon and explain. Okay, the answer there should be yes, this compound that is above is a hydrocarbon. And the explanation is that it contains hydrogen and carbon atoms only. Here comes that keyword now. This keyword is very, very important. It contains hydrogen and carbon atoms only. That makes it a hydrocarbon. A hydrocarbon is going to be an organic compound that contains hydrogen and carbon atoms only. There must be no other atom besides hydrogen and carbon. It's there in the word hydrocarbon. Hydro, short for hydrogen, carbon, telling you that there is also a carbon there. Okay, so that was our baseline assessment. Those are questions, just simple questions that we are asking to just ascertain whether people know what is needed for us to be able to move on to this lesson or today's lesson. Okay, right. So for today, our terminology or things that we need to know today. Today we want to look at defining a saturated hydrocarbon, defining an unsaturated hydrocarbon, and defining a structural isomer. Those are the three things that we need to be able to be familiar with. Those are the three terminologies that we need to be familiar with for today. Right, so we define a saturated hydrocarbon as a hydrocarbon containing only single covalent bonds. You'd remember that last week we spent some time speaking of covalent bonds. The reason why we did that is because they become important when they are mentioned in definitions. So that is why it was important last week that we understand what we mean by covalent bond, where we say it is a bond where there is a sharing of electrons. So we say a saturated hydrocarbon. This is the hydrocarbon containing only single covalent bond between the carbon atoms. And if we're going to put it simply grade 12 for our level, a saturated hydrocarbons, those are alkanes. Alkanes are the only hydrocarbons that have single covalent bonds. So alkanes are saturated hydrocarbons. So when someone is asking you a saturated hydrocarbons, you should be thinking of an alkane. Alkanes are saturated hydrocarbons. So this is just another way of just taking a shortcut and thinking about it in a shortcut manner. You're saying alkanes, they only have carbon and hydrogen atoms, right? And they have single covalent bonds between the carbon atoms. Therefore, they must be what? Saturated hydrocarbons. And we define unsaturated hydrocarbons as hydrocarbons containing double or triple covalent bond between the carbon atoms. So there is a sharing of these electrons there, right? Since we are saying covalent bond, but they are double or triple covalent bond. You'd remember that we spoke of double bonds last week. We also spoke of triple bonds last week. So double bonds, we said last week, they look something like this. So if we have a double bond here, you are going to say this is an unsaturated hydrocarbon. If you have a triple bond, you are going to say again this is an unsaturated hydrocarbon. So simply put, again, you would say saturated hydrocarbons, these are the alkenes and the alkynes. The alkenes and the alkynes are your unsaturated hydrocarbons. So it should be very, very simple to remember these things, grade 12. It should be very, very simple to identify a saturated hydrocarbon, because when you are looking for a saturated hydrocarbon, you are simply looking for an alkane. When you are looking for an unsaturated hydrocarbon, you are simply looking for either an alkene or an alkyne. So it should be simple to identify this. Okay, another thing that we should be able to define are structural isomers. So we are going to define structural isomers as organic molecules with the same molecular formula but different structural formula. Okay, so I'll quickly make an example here. If I look at this structure, simply draw a structure of an alkane with 4 carbons. It will look something like this. Okay, and then I will have again a structure that looks like this. A structure that looks like this, where I'm making all carbons happy by giving them 4 bonds. Now, if you would change this or write a molecular formula for this structure, you'd say this is C4H1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then let's look at the molecular formula for this structure. It will be C4 again, because 1, 2, 3, 4, okay? And then let's look at the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, also H10. But when you look at the two structures, they are not the same. When you look at the two structures, these two structures are not the same. But what is the same about these two organic compounds? They have the same molecular formula, but different structural formula. So that makes them isomers. So that's what we call isomers. Isomers are organic compounds that have the same molecular formula, but different structural formula. So these, when you look at their structures are completely different. This structure has a connection of a chain of 4 carbon bonds. But here you do not have a chain of 4 carbon bonds, because this one is not connected directly to this one. So it only makes a chain of 3 carbon bonds. So this structure is not the same as this structure. This structure has an attachment of something that is being attached there. But when you write their molecular formula, you find that the two molecular formulas are the same. So you are going to call this what? Structural isomers. They are organic molecules with the same molecular formula, but different structural formula. Okay, so grade 12, there are 3 types of structural isomers, okay, that you need to know. You need to know that there is a chain isomer, there is a positional isomer, there is also a functional isomer. Okay, right, so chain isomers, okay, they also will have the same molecular formula, right, but different structural formula. But now we are being specific as to say, what is it that is different about the structure? Okay, so you say chain isomers have the same molecular formula, but different types of the chain. So that's what makes the structure different, is that the chain is not going to be the same, or the parent chain. The parent chain is not going to be the same. I'll come back to this one a little bit, as I will refer to the previous example on it. Okay, here you're going to have another one, which is positional isomers. Positional isomers have the same molecular formula, but different position of either the side chain, a substituent, or a functional group on the parent chain. So in positional isomers, one of the things, either the side chain there, or a substituent, which could be a halogen, or a functional group, which could be an alcohol, a functional group. Then if it is not in the same carbon, then you are saying the position of the functional group is not in the same place. However, if you check your molecular formula, it should be the same. Then you are going to call this a positional isomer. Okay, then the last one is going to be what? The functional isomer. Functional isomers will have the same molecular formula, but different functional group. If you remember last week again, when we were doing the table where we were identifying our homologous series, I said to you that aldehyde and ketones are close together because they are friends. I said to you carboxylic acid and esters are close together because they are friends. Those are functional isomers. So what I want you to know and keep in your head right now, grade 12, is that I have two pairs of functional isomers that I need to be aware of as a grade 12 learner doing technical science. One, aldehyde and ketones. These are functional isomers. So if I have an aldehyde with 4 carbons and a ketone with 4 carbons, definitely those two will have the same molecular formula. They will only differ with the what? The structures. And what would differ by the structures? It will be the functional group. Therefore, they are called functional isomer. Another pair would be the carboxylic acid and esters. Another pair would be the carboxylic acid and the esters. Same thing again. If I have 5 carbons in my carboxylic acid compound, and then I have 5 carbons in my ester compounds, definitely those two are going to have the same molecular formula. They will only differ with what? The functional group. Where is the functional group? The other functional group will be making a carboxylic acid. The other functional group will be making a what? An ester. Therefore, these are functional isomers. So if they say in a question that arises that say look for the functional isomer of compound A, and you find compound A to be an aldehyde, that means your answer that you are looking for should be what? A ketone. Very, very simple there, grade 12. If maybe they say look for a functional isomer of compound B maybe, and you find compound B to be an ester, it means the functional isomer you are looking for should be a what? A carboxylic acid. That's how you should find it, because you know that esters go with carboxylic acid in terms of being functional isomers. Aldehyde go with ketones in terms of being functional isomers. Okay, so I want to ask you to simply look at this definition here of a parent chain. This grade 12, I should say, is an informal definition. It is informal because this definition is not going to be asked, it's not part of our examination guideline. But it's important that we understand and know what a parent chain is. A parent chain is the longest continuous chain of carbon. So any connection of carbon connected to another carbon connected to a carbon, this we say is a parent chain. If we have, for example, a carbon connected like this carbon here is no longer forming a part of the parent chain, because it is not directly connected to all these carbons. Okay, it will make a side chain. It will be this side chain 1, 2, 3, 4, 5. Okay, or this side chain 1, 2, 3, 4, 5, 6. But it's not going to make this parent chain 1, 2, 3, 4, 5, 6, 7, 8. Okay, even though we only go up to 6 carbons, but I'm just making an example for you. Okay, right. Here's how I remember it. What I say to myself is, I will always trace out my parent chain. The largest number that I will get to without having to pick up my pen that I'll be using to trace out, that will be my parent chain. How so? If I trace from here, I will go 1, 2, 3, 4, 5, 6, 7, 8. Okay? If I trace from here and I go, there is no way I can continue tracing out and even reach this carbon without doing what? Picking up my pen and doing this. That's why it cannot form a chain. But if I do this and I decide to take a corner, let's check. 1, 2, 3, 4, 5. Only 5. Okay? Here I have 8. Here I have 5. If I trace out this here and I take a corner this side, I can do 1, 2, 3, 4, 5, 6. Here I only have 6. So the parent chain will be the longest continuous chain, the one with the larger number. In this case, it is 8 carbons. 8 carbons will form our parent chain. It is extremely important that we are able to identify the parent chain, grade 12. Okay, so with that being said, I want to go back to a chain isomer here to say, if you look back at this example that I made here, the parent chain of this compound will be 4 carbons, which will be a butene. And the parent chain here can only be what? 3 carbons, which will be what? A prop. So that then tells us that the difference with these two structures is their parent chain, is their chain. So it means that these are chain isomers. That's the type. Out of the 3, they are not positional isomers because there is no position of anything that has been shifted here. They are not functional isomers. They belong within the same functional group, which is alkanes. Okay. However, they have different parent chain. Therefore, they are chain isomers. Okay. Right. All right. So we get right into the big deal now. The IUPAC naming, grade 12. Now, this is very, very important, grade 12. Being able to name your organic compounds. So we're going to be spending a lot of time here. Okay. So what I've tried is, I've tried to sort of summarize the IUPAC naming in terms of steps. Steps for naming an organic compound. And if you follow these steps, you can name almost any organic compounds. These steps, in conjunction with the table that we are also going to be looking at. Okay, so what steps should you look at when you are naming? Step number 1, grade 12. I want you to make sure that you are able to identify the parent chain. Always be able to identify the parent chain when naming. The first thing that you should do, let's identify the parent chain. Step number 2, once you have identified your parent chain, I want you to number the parent chain forward and backwards. Now, strategies in this regard could be different. Some people only number once. They look for the chain where the substituent is at the shortest side, then they number from that side. I find that to be complicated, if I'm being honest with you, grade 12. However, you do what you are comfortable with. I choose to number forward and backward on the parent chain. Only once I've numbered, I'll be able to decide which numbering system I'll be choosing. Okay, maybe you'll see as I name what is it that I'm talking about. Okay, step 3, you must then, after you have numbered, identify the homologous series from which the compound belongs. So the compound we are talking about, from which homologous series does it belong? This is going to help us with how our name ends. When we are naming the name, it's going to help us tell us how should the name end. Okay, and then step number 4, you start naming the compound. And how do you start naming the compound? You start with the number of carbons. If you have 3 carbons, you are going to call it prop. Okay, and then from there you are going to ask yourself the type of bonds between the carbon atoms. If you have only single bond, it should be an. Next to prop, they should be an. But if you have double bond, it means next to prop, there should be an in. Okay, and then if you have single bond next to prop, it should be an. If you have double bond next to prop, it should be in. Okay, and then if you have triple bond next to prop, it should be I. Okay, so that's how you would know that. Okay, now I'm doing the type of bond when naming. Okay, and then the last part, you are then now going to look at what? The name ending. The name ending. Okay, if they belong to alkanes, then the name ending should be ane. If they belong to alkenes, then the name ending should be in or ene. And if they belong to alkynes, then the name ending should be I, like that. Then from there, you then ask yourself a question: do I have attachments? And if you do have attachments, then you will put them there. The reason why we're looking at these steps, grade 12, is because when questions of naming are asked, when they mark them, they give them part markings. So you will have a mark for just being able to identify the number of carbons and naming it, that it's going to be a prop or prop, and the number of carbons and the type of bonds and the name ending. For this part, even maybe without indicating the attachment, you can get marks from there. So we should be able to do it part bit by bit. Take each part at a go, then that is going to help us. Okay, this will make more sense once we start doing it. But before we can do it, great talk, I want us to look at this table that I want to accompany the steps that we have just looked at. Okay, so here's the table here that I spoke of last week. Again, I called it the R5 catch table. This is my table that I use to always remember the 9 homologous series, because it's very, very difficult to remember these 9 homologous series for some of us. So what I just say to my head is R5 catch. No one should be able to forget this. This is simple. R5 catch. What does R5 catch stand for? R5 catch tells me that I have a homologous series, 5 of them starting with the letter A, and then the rest of them start with the letter K, E, C, and H, making R5 catch. It should be simple. I hope it is as simple as that. So what I want you to do, great talk, is you must familiarize yourself with this R5 catch table and try to use it. What I always advise is that learners must memorize this table so that they are going to use it. So every time they are writing a question paper that has paper 2 or organic chemistry in it, before they write, they should draw the R5 catch table on the side, because every time you name, you need to have your R5 catch table with you. So the R5 catch table goes as follows. You are going to have the homologous series, and then you are going to have the structure of the functional group. What is the structure of the functional group? Therefore, the structure of the functional group is there to help us identify. By looking at the structure, immediately I see a triple bond, I can identify the homologous series. By looking at the structure, immediately I see an OH, I can identify that the homologous series is alcohol there. So you need the structure of the homologous series in your R5 catch table. Again, remember, you are memorizing this table. It is important that each and every one of you memorize this table, okay? Or whatever table that you have been taught in class that can also help in this regard, okay? What I want you to also memorize is the name ending to say. If I have identified that the homologous series is alkane, then the name ending here, ane, is what goes with alkane, okay? And then if I've identified that I'm dealing with an alkene, the name ending here is dash in. Okay, dash in. Sorry, here there's a mistake. Here there is no dash here. Here it's in, there is no dash, right? The dash in here represents something. It's especially important that it's dash in. Dash in tells us that if I am naming an alkene, I must always remember to put a dash and a number. What is the number for? The number is to indicate the double bond, to tell me in which carbon will I find the double bond. Will I find it on carbon number 1? Will I find it on carbon number 2? Will I find it on carbon number 3? So usually our name will be maybe prop-2-in. That tells us that on carbon number 2, there is a double bond. That's why you say dash in here. And then you will also have a dash ine. A dash ine is for alkynes with triple bond, looking at the structure. And alcohol going along there, dash all is their name ending, right, to indicate that the OH is on which carbon. Dash all there is the name ending. So you know by looking. So it tells you that if I am giving the name, if I see the name all, I know the homologous series is alcohol. If I am given the structure, if I see the structure OH, then I know the homologous series is alcohol. This table is extremely important. I cannot stress enough how important this table is for you to be able to answer questions on question 2, paper 2, grade 12. For you to be able to pass question 2, paper 2. All the answers are just right here in this table. All the answers, or at least 90% of the answers or questions that are going to be asked on question 2, they are just here in this table. You are asked to identify homologous series, you look at the structure or you look at the name ending. You are asked to identify, you look at the structure, you look at the name ending, you identify the homologous series. It becomes extremely important if you use this R5 catch table. Okay, so we continue there. We have A number 5, which is an aldehyde. Its structure, I see it by having what? I always say double bond O on carbon number 1. Double bond O on carbon number 1 with the name ending al. Al has no dash here. The reason why al has no dash is because al is always going to be on carbon number 1. This structure should always be on carbon number 1. We discussed this last week. Ketones, they are going to have double bond O between 2 other carbons. They should be surrounded by 2 other carbons. So if you see double bond O surrounded by 2 other carbons, you know it's a ketone. Its name ending should be -O, meaning that you should identify in which carbon are you going to find the C with a double bond O. Okay, and then from there, E is for esters. And then in the esters, you are going to say here, I am looking for C double bond OO. Okay, but this O double bond OO must also be surrounded by 2 other carbons. There must be another carbon here surrounded by 2 other carbons. It's in between. It's naming there, it's O8, and this O8 has no dash. It's O8 and this O8 has no dash, because you don't need to indicate where the COO is when you are doing the what? The esters. And then C, carboxylic acid, is for C. Here you are going to find it with C double bond OO, as it's C double bond OO here, which reminds me here that we said these are what? These are isomers. Last week we were calling them friends. This week we are calling them isomers. These are isomers. What type of isomers? Functional isomers. So for carboxylic acid, you will find C double bond OO, and that is always going to be on what? Carbon number 1. Carbon number 1, the C double bond. That makes the name ending to be what? Oic acid. It's oic acid, and that's how we pronounce it. And lastly, the H on our R5 catch. The H stands for the haloalkanes. And how are we going to see the haloalkanes in the structure? We see that there's a structure that has a X, right? Or has an attachment of X. In this case, X could be a chlorine, it could be a bromine, it could be a fluorine, and it could also be what? An iodine. Okay, but now here I have to say this for here is not necessarily the name ending, because this does not come at the end of the name. Since they are haloalkane, their ending will be ane as well. But at the beginning of the name, since we treat these as attachment, for chlorine we have chloro, and for bromine we have bromo, for fluorine we have fluoro, and for iodine we have iode. So that's how we are going to indicate these things. So this table becomes extremely important. I cannot stress enough how important it is for you to memorize this table. And I need you to memorize this table. I always say memorize this table and be able to draw this table within 3 minutes. Be at most 4 minutes, so that you do not waste your examination time trying to draw this table. So memorize it and be able to draw it within 4 minutes, so that before you start writing, you draw this table, you put it aside, and you are just going to refer to it as you answer questions. If you do that, trust me, I promise you, it is going to help you, and it will help you a lot, being able to do this R5 catch table here. Okay, so let's try and take an activity and try and name a compound, following the steps that we have talked about, and also looking at how we would use a table to answer certain questions. Okay, so let's look at the structure here. They are saying to us, name the compounds in this or give names of the compounds in the structural formula. So these are the compounds that are in structural formulae, and we must name them. Okay, step number 1 says what we should do. We should identify the parent chain. Well, in this case, it's simple. It's just this straight carbon-carbon chain. Okay, step number 2, I've identified that this is my parent chain. Step number 2, I now number forward and backward. I say 1, 2, 3, 4. 1, 2, 3, 4. Okay, I have 4 carbons. Okay, now after that, I have to identify to which homologous series does this compound belong. There comes what? My table, R5 catch table. I go check the R5 catch table. I say, okay, according to the R5 catch table, I only have single bonds here. Okay, according to the R5 catch table, I only have single bonds here. Which one only have single bonds? It's the what? The alkane. So the alkane is the functional group, or the homologous series. the alkane is the homologous series to which this structure belongs. So this is an alkane. So I now know this is an alkane. Okay, from there, now I can start naming. How do I start naming? Number of carbons. How many carbons do I have? 4. And what is 4? 4 is beauty. Second question, what is the type of bond between the carbon? It's single bonds. Single bonds, it's an. Okay, name ending here, they are alkane, and name ending for alkane is ane. So I just put an E here. Okay, and the next question, do I have attachments in this? I do not have attachment, therefore this name is fine. Butane it is. So this must be what? A butane. Okay, all right. Let's try one that is a little bit tricky to do. Okay, right. So I'll give this one to you for about 3 minutes, and then I want you to try and name the structure for me, following the steps, identifying, and also giving the full name. And I'm going to give you 3 minutes to try and name the structure, and I want to see if you'll be able to name it correctly. Welcome back, grade 12. I hope you've attempted the question, and I hope you're getting it right. Okay, let's check if we've done the correct thing with naming this compound. Okay, remember our steps. Step number 1, very, very important. Identify your parent chain. What's your parent chain? That's the longest continuous carbon-to-carbon chain. Okay, so best thing to do, like we said, you need to trace it out and check what's my parent chain, right? This one here is not going to be straightforward as this one. So if I trace out here, I'll get 1, 2, 3, 4. That's a carbon-carbon. I can go to that one it will not be forming part of the chain. Or I can do 1, 2, 3, 4. Okay, if I try this one, 1, 2, 3, definitely not my parent chain because this one has a lesser number. So I have two options now. I can go this way 4, or I can go this way 4. So here's what I always advise. If you have two options and one of them is taking a corner, take the straight chain. Simple, it will make your life very, very simple. That does not mean this one is not going to work. For a person who will take this one as the parent chain, they should be able to get the same answer as us. However, I always advise for us to just simplify our lives and just take the straight chain. If we have two options and one of them is a straight chain, always go for the straight chain. So we will be taking this as our parent chain. So that's step number 1. Step number 2, that's number forward and backwards. 1, 2, 3, 4. 1, 2, 3, and 4. So we've numbered forward and backwards. Then now we have to identify to which homologous series does this compound belong. Then we now use our table. Check our table. Okay, what we have to look at the structure of the functional groups. We only have single bonds here. We only have single bonds between the carbon atoms. We have no oxygens. We have no halogens. Then this must be a what? An alkane. So this belongs to alkanes. Okay, now that we have identified that, now we can maybe start now naming. Okay, how many carbons do we have? We have a butene. Okay, so we say butene. It's 4 carbons. Type of bonds between the carbon atoms, single bonds. So we say an. Okay, name ending for alkanes, A. Okay, so we just simply come here and put what? E. So we have a what? A butane. Okay, last question. Do I have an attachment? An attachment would be anything that has attached itself to what? To our parent chain. And this thing is not part of the what? Of the parent chain. Or it's not a hydrogen or oxygen or a halogen. This could be considered an attachment. Do I have an attachment in this case? And the answer to the question is yes. I have this thing here that has attached itself to my parent chain. Okay, so what do we call this attachment, grade 12? This attachment, grade 12, is called a what? A methyl, right? It's a methyl. This is a methane that is short of one hydrogen. I mean, if it was 4 hydrogen, it would have been a methane. So it is short of 1 hydrogen, so it needs to attach itself to something. Therefore, we put an ion in it, and it becomes a what? A methyl. So we can have this attachment. We can have a methyl, or we can even have an ethyl. Okay, so also watch out for attachments such as an ethyl. Okay, so that's where we will have another carbon here. Okay, then that will form an ethyl. Maybe if there was another carbon here, there was another carbon here, that will make 5, 5. So it will make our attachment to be what? An ethyl. Okay, so as we continue, question, do we have an attachment? And the answer is yes, we do have an attachment. Only now I need to stress about the numbering now. Okay, at least I have collected these marks. Even if I mess it up from here, there is a mark here by now. I am sure. So now I can stress about the numbering. Okay, now that I have to put this attachment, what is the attachment? The attachment is a methyl. All attachments when naming, they come at the beginning of the name. So I can't put it here, I have to put it here. So I'm going to say methyl. Okay, right. Now I have the methyl. I have to identify on carbon number what will I find this methyl, because whoever comes and read my name must be able to reproduce the structure exactly as it is. So I have to tell that person, on carbon number what am I finding this methyl attachment? That's when I have to choose the numbering system. Now, how do I choose the numbering system? I can either go with the top numbering system or the bottom numbering system, grade 12. And how do I choose? I'm going to choose the one that has an attachment with the lowest number. Okay, I'll repeat myself there. I am choosing the numbering system that has the attachment with the lowest number. That's why I number forward and back. Now I look at the carbon that has an attachment. Here is the carbon with the attachment, right? Which numbering system has the lowest number between the two. If I go with top numbering system, I get 3. If I go with bottom numbering system, I get 2. This is the numbering system I will choose. Therefore, it means the attachment is on carbon number 2. So it's 2-methyl butane. That should be the name that I find when I name this compound. Okay, so it should look something like this. This one should be a butane, as we said, and the solution for this one should be a 2-methyl butane. That's how you name grade 12. So you want to do more of these exercises. You want to do more, as I'm going to be trying and showing you. The best way to know and be able to do this is by doing and answering a lot of questions. Let's check here. Let's answer here and let's try and name these ones with this time that we have. We're going to try and name them as quickly as possible, and let's see if we can name them correctly. Okay, so we're going to only name the ones in structures. Okay, so because the other ones are already in named. Okay, so we're going to start with C. Let's quickly name C following our steps. Step number 1, parent chain, straight chain, simple. Step number 2, number forward, backward. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and then step number 4, identify the homologous series. What do I see here? I see a C double bond O. It's on carbon number what? It's on carbon number 1 according to the bottom numbering system. So this must be what? This must be an aldehyde, right? Now comes the use of the table. You cannot do this without knowing the table. Okay, I'm able to do it because I know the table. If you don't know the table, memorize the table, put it next to you every time you're answering, you are using it. Okay, so it's time to start naming. 4 carbons, that's a butane. Type of bond between the carbon atom, it's single, so it's an. Name ending of aldehyde is al. Okay, do I have attachments? And the answer to the question is no. Therefore, my name becomes what? Butanol. Okay, so the butanol, you don't need to stress about the numbering system here unless you have an attachment. If maybe you had an attachment here, okay, on carbon number 2, then you will stress. But again, you don't need to stress about it because this one should always be on carbon number 1. So when you are doing with aldehyde, you should make this one always carbon number 1 because it's a functional group, and the functional group will always take preference over the methyls and the ethyls. Okay, so this one should not stress us. I should have started with B. B comes before C, but let me go straight to B quickly. So we are going to say here again, look for parent chain. It's a straight chain. Number 2, number forward and backward. 2, 3, 4. 1, 2, 3, 4. Okay, so identify homologous series. There's an OH. This must be an alcohol. Okay, let's start naming. 4 carbons, that's butane. Okay, type of bond between the carbon, that's single, so it's an. Okay, and then name ending for alcohol is all. But remember, the all has a dash, meaning that it must be indicated on which carbon will I find the OH. Okay, so that means now I must then choose again the numbering system. Which numbering system? If I counted like this, that will give me OH on carbon number 4. But if I count like this, that will give me OH on carbon number 1. I want to choose the numbering system that is going to give me the OH with the lowest number. So I choose the bottom one. So it becomes butan -1-all. That becomes my name there. Okay. Another person could argue that this is just butanol because it's on carbon number 1. However, I always advise people to always indicate whether it is obvious or not. Okay, so we go to D there, and D we have 3 carbons here as our parent chain. We number it 1, 2, 3, 1, 2, 3. You do not take these steps for granted because they might seem like they're simple. Always follow the steps. Do them even if it's simple. Okay, identify homologous series. I see a double bond. That means this is an alkene. Okay, so if this is an alkene that's named 3 carbon, must be a what? Prop. Type of bond between the carbon atoms. It's a double bond. So I cannot say prop-an. So this time around I must say in. Okay, But in always goes with a dash, if you remember, on name in, meaning that I must indicate on which carbon will I find this double bond that I'm speaking of. It's on carbon number 1 according to the top numbering system, because I cannot choose the bottom one. It gives me it on carbon number 2. I want the lowest number. So it's going to be prop dash 1 dash E, which again also could be argued as propene, but I always advise people to always identify. Okay, I'll quickly run to F there. Okay, parent chain, straightforward, easy. Numbering forward, 1, 2, 3, 4. Backwards, 1, 2, 3, 4. Okay, so we are going to say here we have 4 carbons. Let's identify. I see a PR. Okay, a PR tells me I'm dealing with a what? A haloalkane. A haloalkane here. Okay, so if I'm dealing with a haloalkane, so let's start naming 4 carbons. This could be again a what? A bute. Type of bond between the carbon, single. So it is an. Name ending for haloalkanes. Well, they also end with an or a, okay, because they are alkanes with halogens in them. So the name ending will be haloalkane. However, I'll look at this one as an attachment. So I'll put it at the beginning of my name as I do the methyls and the ethyls. Okay, so I should put and say I have a PR, which is a bromine. And how do I put it? I write it as a what? As a bromo. You would remember we said we have what? Bromo, fluoro, iodo, and chloro. So I will write this as a bromo. Write it at the beginning of the name because I am treating it as an attachment. Now, if I am treating it as an attachment, that means I must then identify on which carbon will I find it. On carbon number what is the PR? Because it's possible that it will be on this carbon, it could be on this carbon. Are we together? So again, I want that when I give someone this name, they must be able to reproduce this structure as it is. Okay, so I can now have to choose now. Top numbering system gives it at 1, 2. Bottom numbering system gives it at 1, 2, 3. Which one has a lesser number? Top numbering system. So I write 2. 2 dash bromobutane should be the name of compound F. 2 dash bromobutane there. Okay, and then let's go G. Okay, G looks similar to B, but we'll see. Then we take the parent chain there and we number forward, backward quickly there. 1, 2, 3, 4. 1, 2, 3, 4. Okay, then from there, identify the homologous series. I have an OH, here it is. Then it means this is an what? An alcohol. Okay, if this is an alcohol, then I can start naming. Okay, they have identified the homologous series. 4 carbons. 4 carbons is bute. Type of bond between the carbon is an. Okay, name ending for carbon is on with a dash. Remember, dash is to indicate on which carbon will I find the OH on carbon number what. Okay, again, once I think of a dash, then I must choose a numbering system. If I go with top numbering system, it gives me the carbon with the OH on carbon number 3. You see, 1, 2, 3. But if I go with the bottom numbering system, it gives me the carbon with the OH on carbon number 2. 1, 2. Which one is the smallest? Number 2. Therefore, dash 2 dash all. Extremely simple this thing of naming, grade 12. It is extremely simple this thing of naming. I go to the last one, which is H. Okay, H here, parent chain here, and then what do I do with the parent chain? I number forward and backward. 1, 2, 3, 4. 1, 2, 3, 4. Identify the homologous series. Go to my table. I see a C with a double bond O as E, and it is in between 2 other carbons. What is this? This must be a ketone. That R5 catch table tells me all of this information. This must be a ketone. Okay, so let's name the ketone. I'll put the name of the ketone here. Let's name the ketone. Okay, it's 4 carbons, so again it must be what? A bute. type of bond between the carbon. Remember, we're looking between the carbon, not anywhere else, between the carbon. It's single bond, so it must be butane. Okay, name ending for ketones, its own. Okay, so its own, so it will be butanone. But if I remember, own in my R5 cache table has a dash. It's a dash own. That tells me that own must be indicated. To which carbon do I find the C with a double bond O? Again, that tells me I must go back and do what? Choose the numbering system. Do I use top numbering system or I use bottom numbering system? Okay, so I check. Top numbering system gives me the C with a double bond O on carbon number 1, 2, 3. Bottom numbering system gives me the C with the double bond on carbon number 1, 2. Which one do I choose? The lowest one. So bottom numbering system. So this is going to be butan-2-O. Butan-2-O becomes the name of this compound. Okay? Now, before I move on to the next activity, grade 12, I want us to take a look at G and B. And I want us to quickly try and find the molecular formula for each. So I'll put the molecular formula for B here. And then I'm going to say this is C4. Okay, and H, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10 with an oxygen. And then let's do for G. Okay, C4 again. And H, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. H10 with an oxygen. So what are we saying here, grade 12? We are seeing two structures that are having the same molecular formula. Two structures that are having the same molecular formula. But when you look at the two structures, they are not the same. Even their names are telling you the structures are not the same. Here, the OH, the carbon with the OH is carbon number 2. Here, the carbon with the OH is carbon number 1. So the two structures are definitely not the same, but they are what? Their molecular formula is the same. So what do we call these two structures? They are called isomers. What type of isomers? Positional. They are positional isomers. Why are they positional isomers? They have same molecular formula, but different position of the functional group. The position of the functional group here is on carbon number 1. Here it is on carbon number 2. Okay, let's quickly look at these two. We look at this one and this one here. Let's do the molecular formula for this one. It's going to be C4, H1, 2, 3, 4, 5, 6, 7, 8, H8, and then oxygen. So this is for C. And let's look for H. C4, H1, 2, 3, 4, 5, 6, 7, 8, H8, H8, and then oxygen. What are we seeing again here? Same molecular formulas. But what about the structures? The structures are different. So what are we going to call these ones? We're going to call them isomers. Are they also positional isomers? The answer is no. It's not the functional group that is different here. Not the position of the functional group that is different here, excuse me. It is the functional group itself, the actual functional group. So we are going to call these ones what? Functional isomers. So that's how you identify functional isomers. The moment I saw an aldehyde and a ketone, I said, and they all have 4 carbons. I said, definitely these ones are isomers. Okay, so that's how you also identify isomers and also how you name these compounds. Grade 12. I hope this issue of naming is helping us. So these are some of the answers that we were working on here. And then 2-bromobutane, butane-2-ol, butane-2-O is what we found also there as we were naming these compounds. Okay, so I also want us to name this one, grade 12. Let's try and name the structure here for our next activity. Okay, so this again is a structural formula. What do we do with it? We identify the parent chain. So let's identify the parent chain here. The parent chain is going to consist of carbon number 1, 2, 3, 4. It ends here. It is also again what? 4 carbons. So what do we do with the parent chain? We are going to number it forward and backwards. 1, 2, 3, and 4. 1, 1, 2, 3, and 4. Okay, after we have numbered, we simply do what? We are then now going to simply identify the homologous series from which this compound belong. To which homologous series does this compound belong? Go back to my I5 catch table, look for the structure that is similar to this one. I see a C double bond OOH on carbon number 1. So this must be a what? A carboxylic acid. This must be a carboxylic acid. So naming it now becomes simple now. How many carbons am I naming? 4. 4 is bute. Okay. It's not always bute, by the way. It could also be prop and pent. Okay. All right. So you have 4 here. 4 is bute. Type of bond between those carbon atoms. It's single, so it must be an. Okay. Now name ending for the carboxylic acid. If you remember from our R5 catch table, we say they end with oic acid. They end with oic acid. So we are going to say butanoic acid. Okay, and the numbering system does not become important unless maybe if we had an attachment of a methyl here or an attachment of an ethyl, then we'll look at the numbering system biasing those attachments. However, when you are naming carboxylic acid, this carbon will always be carbon number 1, so it doesn't matter. So when you are naming carboxylic acid, this carbon will be carbon number 1 because double bond OO is a functional group. A functional group, a carboxyl functional group, if you remember the names from last week. So that takes preference all the time. So again, when we are naming, it's the same as when we are naming aldehydes. When you are naming aldehyde, the CO or double bond O is always carbon number 1. Also here, the C double bond OO is always carbon number 1. You cannot change that. Immediately you change and you shift that, it becomes something else, which will be what? Esters, which is what I want us to quickly talk about here with some time that is left. Let's quickly speak of esters, because naming of esters is tricky business to a lot of people. Okay, let's quickly have a structure here of, let's say, a carbon like this. Okay, let's have a structure like this. Okay, right, so let's make carbons happy. Let's say we had a structure like this one, grade 12, and let's say they said to us, let's name this structure. Okay, let's say they said to us, name this structure. Okay, so how do we go about naming a structure like this? Well, here you are not going to be identifying a parent chain and numbering and doing all those things. Why? Number one, you're not going to have attachments on esters. That's number one. Number two, you have 2 different chains. Okay, I'm going to now explain what do I mean. To form esters, there is a reaction that happens. It's a reaction between an alcohol and a carboxylic acid. So an alcohol and a carboxylic acid will give you an ester. Alcohol plus carboxylic acid gives an ester. So this ester, as it is, it was an alcohol that was added to a carboxylic acid. Very, very important. For us to have an ester, we add alcohol plus carboxylic acid. So when we're naming the ester, we have to think of that. We have to think and say, the first thing we must identify is the alcohol. Then after identifying the alcohol, or what used to be the alcohol and what used to be the carboxylic acid, then that is going to help us name very, very simple. And how do we do that? Again, it's just a simple step that you need to do. What you need to do here, you go to the carbon with the oxygens, 2 oxygens. One of them will be bonded to another carbon, and the other one will be double bonded to only one carbon. Go there and just put a separation line like this. What we have done here, we have now separated an alcohol with a carboxylic acid. So the one with a carbon single bond O used to be an alcohol, and the one with the carbon double bond O used to be a carboxylic acid, grade 12. So what you need to now start doing is you need to start thinking, what alcohol was this? Okay, or what was the name of this alcohol that was used here? Okay, so you need to think. If this is only one carbon is a what? A myth. Okay, so it's an alcohol. The name ending or the type of bond should be an, and the name ending of the alcohol should be on. There's no way it could be dash something, okay, because there was only one carbon. So we have a what? A methanol. So the alcohol here used to be a methanol. This methanol was reacted to what? Carboxylic acid. We go back here and count the number of carbons. 1, 2, 3. And 3 carbons tells you this was a what? A prop. Type of bond between the carbon atoms are single, so it's a prop. Name ending for carboxylic acid is oic acid, so propanoic acid. So this used to be a propanoic acid. So for this ester to be formed, a propanoic acid was added with or reacted with a methanol, or a methanol was reacted with a propanoic acid, of course, under certain conditions. Okay, so what did they give? They gave an ester. Okay, and then what is the name of this ester then? The name of this ester should be a combination of the methanol and the propanoic acid, but then naming it within the means of what? Of being an ester. So how are we going to come up with a name? What we are going to do is we are going to treat the alcohol part as if it was an attachment. Okay, then we are going to treat the carboxylic part as if it was the main chain. That is the one that is going to get the name ending. Okay, I hope you get me. So I'll do it for you so that you see. So we treat this carboxylic acid part as if it was the main chain. It's the one that is going to get the what? The name ending. So let's do it. So it was a chain of 3. So it will say it will be a what? A propan, okay, because single bond, okay, and the name ending for esters is OH. We're no longer putting oic acid because we are now naming the ester. So it's going to be a propanoate. A propanoate. So this gets the name ending. So it's treated as if it was the main chain. Then the one that used to be an alcohol, we are going to treat it as if it was an attachment. So this one is then going to be represented as a what? A methyl. So this one becomes a what? A methyl propanoate. Okay? A methyl propanoate. The alcohol is now treated as if it was an attachment, a methyl attachment. Okay? If it was 2, it would be ethyl. If it was 3, it would be propyl. In this case, it could go even to a pentyl, even hexyl, when you are naming the esters. Okay? But most of the time, it ends at propyl. So it will be methyl propanoate. This would be the name of the ester that is that you get when you add a propanoic acid plus a methanol. So this question comes out a lot, grade 12. This question comes a lot. They ask it a lot, and they would say, they would ask it in different way. Sometimes they will give you the name and ask you to draw the structure, which you should be able to do. Sometimes they will give you the structure and say, name it. Okay, and for you to be able to name it, you must be able to realize which one used to be an alcohol, which one used to be a carboxylic acid. So doing that division there is going to help you a lot. Sometimes they don't. They simply ask a question: what alcohol was used? What alcohol was used in the making of this ester? So you should know by doing the demarcation that it was a methanol. What carboxylic acid was used in the forming of this ester? You should be able to say it was a propanoic acid. That's the not alcohol, but the carboxylic acid that was used. Okay. I also want us to again check something here when it comes to these two compounds. We've done the carboxylic acid, we have done the esters. So I want us to check between these two compounds and check something. Let us get their molecular formula again. Okay, here 1, 2, 3, 4. I have a C4. Okay, Then the number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. And you should physically count them like this, grade 12. When you do the molecular formula, you must physically count them. 1, 2. That's why I said it is extremely important to have a structure. Structures, everything revolves around structures. Let's do this one. Number of carbons, remember we're doing the whole thing now. Okay, number of carbons, 1, 2, 3, 4. So it is a C4 also. Number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. It is HH with also 1, 2 oxygens, O2. So what are we seeing again here? We are seeing the same molecular formula. We are seeing the same molecular formula. And what did we say? We have organic compounds that have the same molecular formula but different structural formula. And what do we call these organic compounds? They are called structural isomers. But these structural isomers are specific. What type of structural isomer is this? We must check. Is the chain different here? The chain is not different. Do we have a difference in the position of a substituent, a side chain, or any attachment or a functional group? No, we do not have a difference in the position of the functional group. What we do have is the difference in the functional group itself. So the functional group has a difference here. So we are going to say this is a what? This is a functional isomer, grade 2. This is a functional isomer with the same molecular formula but different structural formula. That's how you see your functional isomer. The naming of esters, grade 12, is very, very important, and it comes out a lot. So that's how you do most of the naming, grade 12. You need to do those steps, okay? Or those are the steps that I usually employ when I'm naming. Firstly, I want to identify the parent chain, very, very important. Number 2, I want to number the parent chain forward and backwards. It helps me a lot. Then from there, I identify the homologous series. And how do I identify the homologous series? The help of the R5 cache table comes in handy to me, that I'm going to look at the structure and say, from this structure, I see that this structure belongs to which homologous series. And once I've been able to do that, then I can start the naming. Starting the naming, basing it on the number of carbons. And then from there, asking the type of bonds, which is usually single bonds. Okay. And then from there, I would say that the name ending. Again, the table comes in handy again. The table is going to help you now to say, if it belongs to ketones, then the name ending must be O. But with a dash, I know the dash reminds me that the name ending is O. That means I must identify to which carbon is the O. It's on carbon number what? That's the only time I'm going to stress about the numbering of the carbons. That's why for me, I just say number forward, backwards. That's the only time I'll only stress about the numbering. I don't want to stress about the numbering of the carbons at the beginning of the lesson, because this is not going to help me with anything. Okay. Right. So here's the answer to that previous question, which was butanoic acid. So butanoic acid is what the name that we're supposed to come up with here. Yeah, that's the name for this structure. Okay, right. So grade 12, I'll give you this as your homework. I want you to go and try and name the structure as your homework. All these structures. So you're going to do for me A, okay, and then you are going to do C, and then you are going to do F. But also after that, after naming the structures, I also want you to try and draw the structural formulas from the names. So given this name, try to draw the structural formula. B, try to draw the structural formula. D, try to draw the structural formula. E. So from the name itself, come up with a structure. So I also want you to try that. But mostly importantly, I want you to do A, C, and F. Try to see if you'll be able to give me the names of those compounds. Okay, right. So I want us to go back a little bit and try to look at what we've covered for the day, right? and what is important. Okay, today, grade 12, we've looked at saturated and unsaturated hydrocarbons. Okay, we say saturated hydrocarbons. These are hydrocarbons containing single covalent bond between carbon atoms. So you will find saturated hydrocarbons looking like this. Okay, only single covalent bond between the carbon atoms. These are said to be saturated hydrocarbons. Grade 12, saturated hydrocarbons can only be alkanes. You cannot have any other. For our level at grade 12 technical science level, saturated hydrocarbons, I'll write it as I wrote it in the beginning. Saturated hydrocarbons can only be alkanes. If you know your alkanes, then you know all hydrocarbons, because only alkanes will have carbon and hydrogen atoms only, and also have single bond between the carbon atoms. Only alkanes. So they are said to be saturated. Okay, and you must also be able to define unsaturated hydrocarbons as hydrocarbons containing double or triple bond between the carbon atoms. So they are going to look something like this. They are going to look something like this. Okay, you are going to say these is an unsaturated hydrocarbon. It contains a double bond between the two carbons. Okay, you can also have one that looks like this. You can also have one that looks like this. Okay, you are going to say this is what? An unsaturated hydrocarbon. This is an unsaturated hydrocarbon. Why do I say it's an unsaturated hydrocarbon? It contains this one contains a double bond. This one contains a triple bond between the carbon atoms. Immediately I see that, I say this is unsaturated. All right. Okay, so you must be able to distinguish between the two. All right. And then the next thing that I want us, or I'm expecting that you should be able to know after this lesson, is the definition of isomers. Okay, isomers are defined in 4 ways, grade 12. Isomers are defined in 4 ways. Number 1, you define a structural isomer, just in general, structural isomer in general. This is when you are going to say these are organic compounds that have the same molecular formula but different structural formula. So it's sort of like the umbrella of all isomers. So that's how you define isomers. So you must be able to define structural isomers. It's like an umbrella of all isomers, organic or molecules that have the same molecular formula but different structural formula. So for you to determine whether something is an isomer or not, you have to do the molecular formula. That's why it is important that you must be able to do the molecular formula. But again, from last week we said, it is not easy to do a molecular formula without doing a what? A structural formula. So again, the structure is important. So the structure over everything. Structures are the ones that are going to help us with everything. So structure, draw a structure, do the molecular formulas, compare them. Once you see the molecular formulas are the same, but you're looking at your structures, the structures are not the same, then you say this is what? Is an isomer. So you have the umbrella of isomers, that's structural isomers. So I'm emphasizing this because people must be aware, or people must be careful as to which definition is being asked. Are they asking you to define a structural isomer, or they are asking you to define the types of the isomers, or one of the 3 types of the isomers, which are the chain isomer, okay, which you will define as an organic molecule that has the same molecular formula but different chains. So the chains are not the same, like the one we had where the chain was a but and the other chain was a what? A prop. So the chains are not the same there. So they can ask you to define a chain isomer. So defining a chain isomer is not the same as defining a structural isomer. That's the thing I'm trying to emphasize here, grade 12. Okay, so it could be a chain isomer, number 1. Number 2, it could be a positional isomer. Okay, the positional isomer, we talk of the same molecular formula, but different position of the substituent Okay, the position of the substituent, or the functional group. Okay, the substituent, the side chain, or the functional group. Sorry about that. The position of the substituent, the side chain, or the functional group. Once the position shifts, then you say this is an isomer because it has the same molecular formula, but it is a positional isomer. That must be clear. And number 3, we talk of a what? Of a functional isomer. Again, cannot stress this enough. We only have 2 pairs of functional isomers. We only have 2 pairs of functional isomers. Those are the aldehydes and ketones. I cannot stress this. People cannot forget this. You can't forget something that you've been told over and over, grade 12. Aldehydes and ketones. And then you have carboxylic acid with the esters. As I've been showing here using examples, these are isomers. They are called functional isomers. They are molecules with the same molecular formula, but they have different functional groups. Their functional groups are not the same. And then lastly, for what I want you to know for this lesson is that are you able to use the homologous series and functional groups to name organic compounds? Of course, with the use of the R5 catch table, or whatever you name that table, because a lot of people name this table, give this table different names. I call it the R5 catch table. Are you able to use this R5 catch table? Grade 12, are you able to draw this table on your own without having to take it from your classwork book or your notebook or from your teacher or from any other book that you've come across? You should be able to draw this table on your own. That way this table becomes part of you, becomes second nature. Then you can be able to do what? To give names, naming without having to go and refer. Being able to identify homologous series by just looking at the structure. Being able to give the name endings because you know this homologous series goes with this name ending. All of this is important for naming, okay? Remember the steps for naming. 1, we identify the parent chain. That's the longest continuous chain. Number 2, we will then number the parent chain, okay? The numbering is different with different people. I prefer that we number forward and backwards, okay? But if you have a different way of numbering, it is okay, it's fine, as long as it works and as long as it gives you the correct answer. I usually prefer numbering forward and backward. It just releases the stress of having to think how to number, because I'll just simply choose at the end. So you number forward and backward. After numbering forward and backwards, then you identify the homologous series. Then from there, you can start naming. And how do you name? You start by naming the number of carbons. You have 5 carbons, it should be pent. Then the type of bond between the carbon atoms, if you have a double, should be in. But in has dash. That means you have to identify where is the in or where is the double bond. If it's single bonds, it should be an. If it has triple bond, it should be ein. Okay? Then from there, you put in the name ending. The name ending, again, is part of the table. So you put in that name ending. And after that, that's when you're going to ask yourself, do I have an attachment? So what can be attachment? Attachment could be methyls. And methyls look like this. It's a carbon with 3 hydrogens. And this carbon must be connected maybe to some other carbon chain. Okay? Then it's a methyl. Or it could be an ethyl. Okay, let me draw it like this. Okay, the way you are used to seeing it. Okay, something like this. Okay, and then hydrogen, and then this carbon will be connected to a carbon chain, a chain of other carbons. So this guy becomes a what? Becomes an ethyl. This could be an attachment. And then another one, an attachment or treated as an attachment could be the halogens, the Cl, the Br, the F, and the I. These ones they could be treated when you are naming. You could treat and look at them as if they were attachments or substituent in your structure there. Okay, so that's our summary, and that's what we expect that you are able to do after this lesson. All right, so we've come to the end of our lesson, grade 12. Join us again next week as we continue doing organic chemistry, and next week we'll be doing physical properties, looking at those boiling points, melting points, viscosity, and the vapor pressures, and how they affect the intermolecular forces, or how the intermolecular forces affect them. Okay, so that is it for today, grade 12. Thank you.